All right, good afternoon everybody. My name is Arkadiy Shapiro. I'm a product line manager at Barefoot Networks, so great to be here at HP Discover. So today we're going to talk about the chip as your canvas and P4 as your pane, leveraging programmable forwarding planes to draw your ideal network. Okay. So before I get started with the use case, maybe a little bit of background about Barefoot Networks, because I think some folks may not be familiar. Company was established about 5 years ago, and the main problem that we set out to fix, that we set out to tackle, is the fact that the networking systems have been really built from the bottom up. So as a result, really the chip, the silicon in the switching system tells the switch operating system how it processes packets. It's fixed function, you really cannot change it. And with all the advancements from SDN, from software-defined networking, all the changes in the control plane, APIs and things of that sort, the data planes really have not kept up. Really, this is the last frontier of software-defined networking that have not been tackled, that has not been cracked. And the vision of Barefoot Networks, the vision of our company and the guiding principle of all the products is that the networking systems really should be programmed top-down. So as a result, the switch operating system or the end user really tells the chip how you should be processing the packets. So the consequence is that you are now in control, right? Whether it's you being the vendor of the networking system or you being the end user who has decided to program the chip by yourself and leverage the data plane programmability concepts. Okay. Now, you might be thinking, this is great, but why would I want to program the chip? Why would I want to change the data plane of the chip? And this sort of dives into a little more details as to why you might want to do that. So first of all, simplification. If you look at the networking systems today, when the vendor gives you a networking system, you have lots of different features. Chances are you're probably not needing half of them, if not more than that, right? We run into customers all the time who are saying, really, I'm only using a small subset of the functionality that the vendor provides to me. So wouldn't it be great that you could just remove that functionality, not only from the control plane, because nowadays network operating systems are fairly modular, right? So they allow you to kind of add and remove components, right? Some more than others, but you could remove that from the data plane as well and reclaim that real estate in the data plane for things that you're actually using. And so for example, right, if you are moving towards IPv6 and you've moved towards an all IPv6 network, why should you be taking up space in the silicon for IPv4 programming? Right? So with the programmable data planes from Barefoot Networks, you can actually do those type of things. Right? So this is about, again, taking the canvas and redrawing the canvas. Right? And in this case, we're doing that using an open source language called P4, which I'll touch on a little bit later. Speed and agility, right? Innovating really with the speed of software. Before, if you needed any kind of functionality, you needed any change, you would have had to wait for a vendor to bring on a new networking silicons. Some network systems vendors actually build their own silicon. Most use what they call a merchant silicon concept, right? To work with other companies to put a silicon from them into their networking products, right? Switches and routers, okay? Going forward, right, scalability. I talked about moving from V4 to V6, focusing on V6 scale versus V4 scale. Perhaps you're in a spine, like layer 3 spine, so you don't need any space for the L2 switching, right? So you could remove or scale that table significantly, reclaim that space for your IPv4 or IPv6 routing, right? Things that were simply not possible before because the data planes were completely fixed. Data plane streaming telemetry, right? Doing telemetry right in the hardware, right? Not talking about sending a bunch of packets to CPU or doing spans or taps with packet brokers. It's about really tracking every packet that's going through your network and reporting only when there's an anomaly, right? And what kind of data you can report is really dependent on the P4 program that you write, right? So really dependent, what is the paint that you're using here on your canvas, right? And finally, future-proofing, right? So customers now, with systems based on the programmable silicon, they feel more secure, right? That the network is more future-proof, that they don't have to rip out the systems and replace it with a new system whenever there's a new requirements that require different type of packet processing. So a little bit of background about the company. As I said, company has been around for about 5 years. Really in 2016, late 2016 is when the actual silicon came out. And from that onwards, we've been building more systems. We actually have lots of Baremetal switching partners as well as OEM partners. I'll talk about those in a minute. And starting, I would say, 2018 is really when we're seeing the ramp in production customer deployments and the ramp of more vendors announcing systems with the programmable silicon inside them, right? The programmable silicon from Barefoot Networks. And so great, definitely 2018 is a very exciting time to be in the space, an exciting time for our company to kind of raise awareness about our products and technologies. Okay. So overview of the entire gamut of products. I talked a little bit about the chip, right? It all started with the silicon, various form factors, various versions of the silicon, go all the way going from the 1.9 terabit, the lower speed version, up to the 6.5 terabit chip. Right? So 6.5 terabit chip really allows you to do 64 by 100 gig ports, line rate traffic with full data plane programmability without any compromise to performance or power or latency. Right? Now, all of this is enabled by our software development environment. So in my daily job, I'm responsible for the roadmap of the software development environment, including the compiler that really takes your P4 program, remember your paint, and pushes it down to your canvas, your chip. Right? And on top of that, we have some additional applications that we've developed. One of them is called Deep Insight. We developed this application from the ground up to really harness the telemetry data that's coming from the chip. And today, when you look at the network performance monitoring applications, really we haven't found anyone that's been purpose-built to handle the data plane telemetry information that's coming from the silicon. So that's why we have a complete software product. Even though that Barefoot Networks has started as a silicon company, we do offer a software product, which is this network performance monitoring system called Deep Insight. Last week we actually had an announcement that it's now entered general availability, so customers are able to order it, try it, and start putting it in production. Okay, and of course, right, the growing ecosystem around data plane programmability, namely powered by this language called P4, right? So P4 is an open source language that lots of people are starting to adopt from academia to industry and beyond. Now, on the chip I mentioned before, right, various versions of the chip, we call it the world's fastest and most programmable silicon. What this means is that really the silicon comes up as a complete white canvas, right? So remember, we have the analogy of the canvas here. The silicon has no clue about L2 or L3, V4 versus V6. Really, it's the P4 program that defines what the silicon does. And when we talk about our PISA architecture, the program independent switching architecture, this is really what it embodies, right? Is the fact that the silicon does not have to be dependent on any networking protocols and encapsulations, right? How the silicon parses packets, how the silicon does routing and switching really is defined by the P4 program. Okay. So again, a few more words on the P4 programming language. Open source language has been around for quite some time. We just had a recent P4 workshop that has gathered more than 100 folks in attendance at Stanford University in California. As you can see here, it is not just Barefoot, it is not just universities, it's a gamut of folks from academia, from operators. We're actually seeing a bunch of operators who are starting to write their own P4 programs to address use cases in their networks around VNF offloading, NFV, mobile core, things that simply they couldn't have done before with their traditional solutions. Right? And of course, systems vendors, chip vendors that are coming on board here as well. Right? In terms of systems vendors, you can see kind of on the left-hand side, folks like Cisco, Extreme Network, Arista. They're all coming out with solution based on this programmable silicon and doing their own P4 programming to really address very custom use cases that they couldn't do before. Okay. So this is another example of fixed versus programmable packet processing, right? So in the fixed chip, all the tables are pre-carved, as I talked about before, right? You have certain logic for L2 processing, for L3 processing, V4 and V6. Really, you cannot change how the packet is processed, and you cannot change the sizing of all the different tables that you have on the chip. And as we talked about, with a programmable pipeline, with protocol-independent switching architecture, chip is really a white canvas, a blank canvas. You can do whatever you want, right? Which is defined by the P4 language. Now, customers here at HP Discover have been asking me, well, this is great, but I'm probably not going to be buying the silicon directly from yourself and start welding it into some PCB board. And no, that's about right. Now, how you can consume this silicon? Well, there's two delivery models. One is going to a traditional switching vendor. Right? Here at HP Discover, HP actually is working with multiple different networking vendors, and there's some innovations that they have in-house. One of those vendors is Arista that HP has a long-standing relationship with. And with that, Arista has announced 2 weeks ago a product called Arista 7170, which is completely vertically integrated system that Arista is providing both the hardware and the software, and they're leveraging dataplane programmability to write a P4 program and address some very interesting use cases that they couldn't have done before. Right? Now, the other scenario is going the route of Baremetal switching, where you get a switch from any of our Baremetal switch partners. Probably folks like EdgeCore, Delta Networks, and Ventec are the most prominent ones. And then you decide which operating system you want to put on that switch in silicon. Right? Operating systems come in various shapes and sizes. There are some commercial solutions. There are some open source solutions. Obviously, with open source solutions, it's more of a do-it-yourself model. You get to do a lot of things. You get to change how the operating system looks and feels. With access to our software development environment, you get to change the P4 program yourself. Right? But of course, right, you do have to have some engineering resources in order to do that. Right? So depending on which customer you are, where do you fall, you can either do everything yourself or work with a vendor to help you with that dataplane programmability. The key is understanding the capabilities that are being brought right now in the industry. Now, a few examples of the Baremetal switches that have the Tofino silicon inside them. Again, folks might be familiar with EdgeCore, and there are a few other examples here as well. And then I mentioned about the operating systems that go on the Baremetal switching. Sonic is an example of an open source operating system. IP Infusion is our longtime partner that we've been working with in terms of a commercial operating system offering. And folks who are used to OEM or typical networking system coming from HP or Arista or other vendors, and they want to try out the white box switching route. Really, they feel very comfortable with IP Infusion because it has a very similar look and feel. But now you get to leverage the power of Baremetal switching, and you can have the flexibility of loading it on multiple different systems. Okay, and there are a few other open source examples as well, including Open Network Linux and Project Stratum, which is a new open source OS designed for SDN environment. That new project that has been started only a few months ago by Open Networking Foundation. Now let's start diving into the use cases. First, if we talk about dataplane telemetry, I mentioned dataplane telemetry at the beginning of the talk, and we go back to network performance monitoring. Today, if you look at network performance monitoring, it is pretty expensive and inefficient. Really, most folks have been doing what they've been doing for decades. Ping, traceroute, SNMP, maybe SFlow and NetFlow. They might be putting things like packet brokers and doing tap and span aggregation. And the problem with that is that really you cannot capture microbursts. You cannot capture microsecond or nanosecond events. Right? All of these solutions, they may be good for security and a few other use cases, but to really detect how the network is performing, to really detect microsecond level events, those solutions simply do not scale. Right? They simply do not work. Right? Especially at today's speeds of 100 gigabits and beyond, right? Starting to look at 400 gigabits. Right? The traditional solutions just simply do not work for tracking network performance. Right? And as a result, right, if you don't have visibility as to what happened, if you don't have visibility as to why my packet got dropped, right, not just knowing that it got dropped, because that's not very interesting, but knowing why it got dropped, you really have no control. Right? You're completely blind as to what's happening in your networking fabric. And really what we set out to answer with our telemetry solution are the following question, right? Which path did the packet take? Which rules did the packet follow? How long was it queuing up on the switch? And who did it share the queues with? Today, all of these questions are practically impossible to be answered. And any switching silicon, any switching system that you take from the market, you really cannot get a clear answer to all of these questions. And with the programmable silicon from Barefoot and also the deep inside application, the network performance monitoring application I talked about, we're finally able to give customers answers to these specific questions. Okay? So again, the first use case that we're talking about is the dataplane telemetry, really tracking every packet from the network. And when we say that we're tracking every packet from the network, it doesn't mean that we're creating a big cache. It doesn't mean that we have to store every packet on the switch. It means that we can analyze every packet and we can only report on those packets. We can send those small digests to the monitoring system, which is deep inside, only when there is an anomaly. So if I have a flow going through the network and nothing is happening, right? Nothing is being queued up, there's no microburst, there's no packet drops, I really don't need to overwhelm my monitoring systems, right? Unlike the traditional solutions of S-Flow and NetFlow, or copying data from span or tap to a monitoring system with or without packet broker, we don't have to send the data when there are no problems, right? We really only send the data, and we don't send the whole packet. We just send a metadata about the packet to the monitoring system when we see an anomaly happening. Right? And anomalies are things like microburst, high latency that goes beyond the defined threshold, packet drops for a variety of reasons, right? Whether it's a tail drop in the queue, or drop because of ACL, or for any other reason that the switch may be dropping packets, right? The reason that programmability is important here is because very few customers actually know what they want to track on. Right? And typically they're used to a switching system telling them, hey, what kind of visibility they can get. However, here, customers can see, okay, what do you want to focus on? You want to focus on latency, or do you want to focus on packet drops? Or maybe you want to get all of that information, right? Because of the programmability, they're able to customize what type of data they're getting, right? And with our reference P4 program, we're giving them an example of how to do that. And then either end customers or the network and system vendors can take it from there and perhaps add their own extensions and do things as they see fit for the specific use cases that they're trying to target. Okay? Now, telemetry is really more than just tracking packets on the switching silicon. We're extending this through our open ecosystems to network interface cards as well. So in this scenario that we've demonstrated at the Mobile World Congress earlier this year, what we've seen is that we're tracking packets not only going through the switches, but also going through smart network interface cards. In this case, our partner, Xilinx, we've demonstrated looking at those packets and inserting particular headers in the packet that track the amount of time that packet spent on the NIC. And especially if the packet is traversing through various different virtual networking functions, it's important to know how much time the packet spent at each VNF, right? So if we're able to do that, if we're able to add this metadata to the packet, and then if we see a latency spike, export that data to the monitoring system, it's really unprecedented visibility that folks, particularly in the VNF deployments, have not been able to get before. Now, second scenario is really emerging protocols. One example is segment routing v6, fairly new protocol. Folks are starting to look at that, traditional kind of scenario. Before you would have had to wait for a next generation silicon for this functionality to be added. We've been able to add it in a matter of days and demonstrate interoperability with another silicon at a trade show floor, right? So pretty impressive. If you think about something that's been around now for some time, VXLAN, folks who are familiar with VXLAN, they know how much time it's actually taken silicon vendors, folks who are building silicon, to get VXLAN right. First iterations just did VXLAN layer 2. Later on, they've added layer 3, but it wasn't quite working. So it's only after 3 or 4 iterations, folks were able to have to get to a production-grade VXLAN deployment. And all of this was because the silicon was fixed. So really, if you made a mistake, if you didn't get something right, and you weren't able to catch that problem early enough, you have to wait for a respin, you have to wait for a next generation of silicon. Right? Again, with programmable data plane, all of that is defined by P4. How you do VXLAN switching, how you do VXLAN routing, right? L2, L3 gateway, how many VTAPs you have, how many VNIs you have, is all defined by the P4 program that you write. Okay. Another case, programmable silicon for packet brokers. So those of you who are familiar with packet brokers, right, coming from various companies, right, such as Big Switch Networks, Gigamon, Ixia, and so forth, really what packet brokers have been doing up until now, they've been doing tap and span aggregation, and sometimes for some advanced functionalities like header stripping, packet slicing, and doing, you know, any advanced tunnel encapsulation, really they had to rely on either servers with DPDK or doing FPGAs, right? All of that drives up the cost and makes that solution a little bit less flexible. So what the programmable data plane really offers you is an ability to take some of this advanced functionality back into the network, back into the switch and silicon, making the solution much more cost effective and much more agile. So we're already working with quite a few customers who are building next generation packet broker solutions that leverage the programmable data plane. Okay. Machine learning, a lot of talk about machine learning, definitely at this trade show floor, you know, yes, newer topic, but with machine learning, we're seeing definitely an increase in data, a need to be able to potentially process packets based on different types of headers that folks have processed before, right? Any custom machine learning protocol where we may be able to do some very custom processing or forwarding of the packets based on that header, the network becomes that much more efficient, right? And again, gaining visibility into the performance of the network. If I have very large workload that are, you know, drawing up the bandwidth, maybe I have some latency spikes, really can give me an idea why my particular workload might be taking a little bit more time than usual. Right? So there are some of the use cases that we're exploring with our customers about how can I make the network actually smarter for machine learning, right? Not just be the same network as it was before, but be a network that's really fit for this particular purpose. And finally, the final use case is VNF acceleration. Right? So those of you who are familiar with the telecom space, lots of custom appliances that we're doing, particularly in the mobile space, doing like things like S-gateway and P-gateway termination. Those appliances have moved towards the virtual space. Perhaps not all of them, but a good chunk of them have moved to the virtual space. But with the virtualization also came another set of problems, right? And as the VNFs have proliferated, some of the traffic that's going to those VNFs perhaps has had an increased latency because you had to go from multiple VNFs, and the solution also becomes a little bit complicated. And certainly we see an opportunity to take some of that functionality, take some of that packet processing back into the network and relieve the load that is being pressed on those virtualized servers. So with Open Networking Foundation, we've actually showcased a use case where we've taken a normal fabric forwarding and we've added some service provider mobile gateway type functionality right there on the switch. So instead of sending all the packets down to that specific VNF, that data, that mobile traffic has been processed directly on the switch. Right? They're therefore saving a good amount of server resources in terms of CPU and memory. Right? So quite exciting new use case. We're working with lots of operators around the world who are trialing this technology and trying to see, right, how they can take some of that mobile packet processing back into the switching data plane. So in summary, if you look at other programmable solutions, starting with GPUs, for example, GPUs have really started with graphics processing, and when folks, companies like NVIDIA have started with those, they typically haven't thought about that, there could be other applications. But later on, folks have discovered that, hey, GPUs could be used for big data, GPUs could be used for virtual reality. And now we're starting to see that they're being used for machine learning applications, for automotive, like self-driving vehicles and so forth. So we see a similar trajectory with the programmable silicon for networking, right? Where we're starting this with the telemetry analytics with just data center switching, and we're seeing this expand to other types of applications that are not just plain type of data center switching, like packet brokers, layer 4 load balancers, and going further towards building a specialized network and interconnect for machine learning, for storage, and beyond. Now, all of these use cases, we're working with a number of open source groups. One of them is P4 Consortium. So the group that is the stewards of the P4 language has a particular working group called P4 App Working Group. And this is where some of these new use cases and solutions are being discussed, and the specifications are being published on their website. And so folks who are trying to implement those, they can see this as an open specification written in P4 for any of those use cases that we're tracking in the industry. So with that, I thank you for your time, and have a great day at HP Discover.